In the 1980s, IBM scientists Gerd Binnig and the late Heinrich Rohrer wanted to directly explore a surface's electronic structure and imperfections. No instrument existed at the time to do this, so they invented one that could, the scanning tunneling microscope, and later the atomic force microscope. More than 30 years later, IBM scientists continue to follow in the footsteps of these two pioneers with the invention of another critical tool for helping us understand the nanoworld.
The thermometry technique that we've been developing is based on atomic force microscopy. In my mind, one of the coolest tools that we have as a scientist. Scanning force microscopy has a very simple principle. You take a very sharp tip, which we can make almost arbitrarily sharp nowadays. You scan it over a surface, and by feeling the surface, you can have a picture of its shape, of its morphology. And this has been used in the last 30 years with better and better and better resolution and accuracy. Now, as soon as we started scanning these sharp tips over surfaces, we also found, in principle, you can attach to the tip any kind of sensor, which you can also scan across surfaces and get a picture of whatever you sense alongside with the structure. Now, temperature came up very early on, but it turned out that to measure temperature and the heat flux between the tip and the surface is not so easy to do with very high accuracy. So that has been relatively slow compared to other scanning probe techniques. Now, in recent years, however, the question from technology was more and more present. People wanted to know what is the exact temperature in my very small, even nanoscale device during operation, and this applies to our processor chips with little transistors, which may have a nanometer scale hotspot in a single transistor. It can also apply to memory cells where we want the heat to happen, in contrast to transistor where it's a nuisance that we've got so much heat.
Okay, the best way to understand how we try to measure temperature on the nanoscale is basically to think about our own perception to hot and cold. So the very intuitive way to understand how we can infer temperature on the nanoscale is to think about the way we try to infer temperature simply by touching something, for example, with our hand. Now, when you are touching something, you're not really directly measuring temperature, but you are sensitive to a heat flux, and very similar, we are sensing heat flux signals on the nanoscale. Now, the challenge in inferring temperature using this kind of heat flux sensing, as with my hand here, is that it can be very easily misleading. So you may, for example, touch materials of different thermal conductivity. Let's imagine this glass here, or the metal. And just by the difference in thermal resistance, you may have the impression that to touch something of different temperature, which is not actually true. Okay, the similar challenge we have been facing on the nanoscale, so we had to distinguish between the resistance to heat flow and the temperature on the temperature. And for this we have invented a new technique which we are calling scanning probe thermometry. In this technique we are intentionally creating a heat flux by self-heating a scanning probe sensor. So there's an electrical voltage bias applied to the scanning probe, which is creating heat very locally above the scanning probe tip. And this heat flux between the scanning probe tip and the sample we are electrically measuring. Just as you may infer temperature using a medical thermometer, where you may have an electrical sensing element which is detecting the temperature of your body. Now, the big difference compared to this macroscopic example where you try to infer the temperature of your body using a fever thermometer is that you cannot equilibrate if you make a form of contact between the sensing element and the body. So we have to measure this temperature in a non-equilibrium situation, and this means we have to know something about the thermal resistance, and this is the big invention, the big step we have done in this technique. So we have found a way how we can simultaneously probe the resistance to heat flow next to the heat flux, and by measuring these two signals simultaneously, we can finally infer the sample temperature locally. Here you can see our scanning thermal microscope as it looks like when it's outside the vacuum chamber. So down here we have the bottom flange with all the feed-throughs for electrical signals for the optical laser beam. Up here we have different kind of positioners, so piezo positioners which enable us to move the sample with very high precision up to sub-nanometer step size. Here we have the cantilever holder where the actually sensing element of our thermal microscope is situated. And on the top part we have an optical beam deflection system, as you may find it also in a regular AFM, to detect the motion of the cantilever, which gives us information about the surface topography.
Our first application that we have demonstrated in the last few months was to measure how hot a nano device gets for what we call the logic application, a transistor. A very small semiconducting structure, and it produces some heat. One of the areas where we are most interested in to go next is very dedicated structures and memories, for example, for what we call a neuromorphic computing. It's a new kind of computing where we replace simple transistors with something which combines both the switch and the memory in a single element. And a lot of these also require the exact control and dosage of heat in that structure during operation.